MDM4U 7.3 Geometric Distributions. Geometric distributions have the following characteristics. The random variable is the waiting time, the number of unsuccessful trials before a success occurs. Outcomes are either success or failure, and trials are independent. So, the characteristics of this type of probability distribution are given by its probability function. We have q to the power x times p, where q represents the probability of failure and p represents the probability of success. So if we have an exponent as a method of writing repeated multiplication, when we have q to the power x, that means that we have failure x number of times consecutively. Think of this as fundamental counting principle, where we have a sequence of events being failures until a success, and we have x failures until a success. Now, if we're thinking of any event where the probability of success is a given value and the probability of failure is a given value, there can be any number of failures possible before a success. So, when it comes to the expected value, our lower limit is 0 because we could have 0 failures because that would mean success on the first trial. But this would go all the way up until an infinite number of failures before the first trial that is successful. So therefore, there's some challenging mathematics to be able to prove that this formula, x times the probability of x, is equal to q over p, but we'll be including a bonus video in the content folder that explains how we go from this expression to q over p, a simple calculation for the expected value. So, if you haven't played the game of Monopoly, getting out of jail in Monopoly, if you are in jail, you must roll doubles with a pair of die to leave. Calculate the probability distribution for getting out of jail in Monopoly in x rolls of the die. So, that being said, rolling doubles. If you can recall our diagram for a grid of one die and another and all of the different sums, across the diagonal you would have 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. That's 6 outcomes out of the total 36 sums, and 6 divided by 36 is equal to 1/6. So that's the probability of success, which implies that the probability of failure is the complement, 5/6. So let's take a look at the probability distribution table. Having 0 failures, meaning success on the first trial, would just be 1/6. And here, with 1 failure before success, 5/6, that's the first event, failure, then a success. It happens roughly this amount of time. 2 would be 5/6 squared to the power 1/6. Now notice, this would mean failure, failure, success. That's why we use exponents to abbreviate this product, but that would be 5/6, 5/6, 1/6 as a product. And then if we had 3 failures before the first success, that'd be 5/6 to the power 3, namely 5/6, 5/6, 5/6, then 1/6. And this is all based on fundamental counting principle, a sequence of events. And with this probability distribution table, notice that there's ... at the end because you could technically go millions of trials without rolling doubles. It's not very likely, as you can see. The probability is getting smaller and smaller as time goes on. And this is better illustrated with a graph. As you see, this decreasing function looks like an exponential decay graph. So, that being said, the probability distribution table is excellent for telling you the exact value. The probability distribution graph is excellent for showing you the distribution of those values and general trends overall. So, that being said, the expected value formula, Q over P, that's failures over success, would be 5/6 over 1/6. And whenever we have a fraction divided by a fraction, invert and multiply. So 5/6 times 6/1, which is equal to 5.